So I'm Likhiz. I'm going to tell you about some work that started my PhD thesis under Irene and with collaborating also with Ricardo. And now we've continued this even though I'm now at Aachen. So I want to talk about this phase separation in heterogeneous fluids, and it'll be, I guess, somewhat similar to the talk of Professor Zaffieri on Wednesday. So first, I wanted to give some physical motivation for why we want to consider these models. And basically, the answer is these types of complex lipid rafts. So the original biological motivation comes from this paper of Simonson and Konen, where they proposed that proteins move along the membrane along these slightly hardened fluid phases. So on the membrane, it's, as this picture shows, there's many different structures. And what they claim is that the way proteins move is because the cholesterol interacts with some of the lipid layers, and it creates a slightly hardened fluid, or a more viscous fluid. And the proteins can sit on top of these rafts and float along the less viscous lipids. So if you look at images for these things, so there was this nice review that I found from 2007, where basically what we're looking at is these model membranes that biologists create in the lab, so these aren't real cells. But what they have is they can dye different portions of the membrane, and they can, the slightly hardened ones come out green, and the more fluid or more liquid or mobile phases come out red. And so you see that there's these slightly hardened, I guess, rafts that they call over here. But around the time that this theory was proposed, there was a lot of controversy because basically it was claimed that this is all just like an experimental, bug based on the fluorescence or something, and that actually in a model cell, this is also a model cell, but under physiological relevant parameters, so if you take the right temperature, right concentration of cholesterol, and all this stuff, then you don't see any phase separation. You just see something that just looks like a regular cell, I guess. And I just wanted to add that in these bars, they're around 30 micrometers. So these cells that they have here are really like around 90 micrometers wide. But later, they did this experiment even more carefully, and they found that there are these very, very tiny domains, right? So on the scale of single nanometers that's in these cells, and this is the actual experiment which verified this. So I took this straight from their figures, so I don't actually know exactly what they're measuring. They're measuring some angle that the light shines off. Is weird, and they claim that if you have a random distribution, you should see a slanted line, but if you see more of these subpixel domains, you should get this straight line. And okay, so their experiments show that you get a very straight line. So these are things in literally like single nanometer scales in cells which are 100 microns. So as I think the talk this morning, that's very, very tiny. So and then recently they've improved their microscopy. So this bar is now 3 micrometers. So they can sort of see these, and now these are actually real cells. This is actually yeast cells that they slice up, and they do this experiment in. And so you can see these lipid rafts within yeast cells at very submicroscopic. So the idea is we want to homogenize all this submicroscopic phase separation, but we want to do it in such a way that, you still see the entire material. Like you don't achieve macroscopic phase separation because, like in this picture, you don't actually see any macroscopic phase separation at a macroscopic level like this. And okay, so we're going to pose this problem as this periodic homogenization problem, where you have a domain, and then you have a cell with potentially different conclusions, where you may have different phases allowed in different portions. Okay. But first, we want to, so the tool that I'm going to use a lot in this talk to motivate a lot of our analysis is two-scale convergence. I just want to briefly review two-scale convergence. So two-scale convergence is a type of convergence that is basically perfect for homogenization because you're testing against these oscillating test functions, which are periodic in the fast variable. But with the cost that you end up going into, you double your domain space. So you have a fast variable with y, which sort of encodes information about the microstructure, and then a fast variable, and then a slow variable x, which encodes information about the macroscopic, I guess, average domain. And so you can say that things weakly two-scale converge if you have this property, and strongly two-scale converge if the norms also converge. And the way I'm really going to use this is this notion of unfolding operator, which is from Chirnescu, Dalmami, and Rizzo, and also separately by Vicentin in the early 2000s, where they basically proposed this operator uf-epsilon as a way to sort of reduce two-scale convergence to normal LP convergence. So this weak two-scale convergence is the same thing as saying that your unfolded function just converges weakly in LP of the product space. So how does this work? It's basically, so given a point xy, your x selects which part of the grid. So you take a grid of size epsilon and you exhaust your domain with it. So there is some region where it intersects the boundary, which you just disregard. And on the region which is completely contained within the material, your x selects which part of the, which cube you're in, and then the y actually tells you which point on the cube you want to select. And okay, so I didn't really define what to do on these extra portions. And that's because generally for the stuff that I do, for the compactness, it really doesn't matter. You choose it, or I choose it, so that the algebra is nicer and I don't have to do too many additional terms. But okay, in more complicated things, it might matter, especially when you consider, when you also want to unfold gradients. Okay, and the main properties that I guess motivate our analysis is this one, that if you have a free energy and which is Q periodic in the spatial variable, and you have, depending on your phases, let's say, then you can write this out using the unfolding operator as a double integral over Q, with the nice part that you no longer have to worry about the deltas in here, and the delta just goes as part of your, I guess, your function, and some extra term which comes from the boundary region. And okay, and then if you're using W1P, then it's also differentiable and Sobolev, where your Sobolev is now in the y variable. So these are some nice properties that you can use to simplify, I guess, equations, to simplify homogenization equations to try to do normal relaxation type results. So I will. So we want to achieve this submicroscopic. We want to homogenize this submicroscopic phase separation. And there are many different models for phase separation, so I'll mainly talk about two different ones. So the classical one is the standard Cahn-Hilliard-van der Waals energy, which is you have a free energy, which encodes the fact that you have wells. So I use two wells here just to simplify the terms that I have, but you can actually do this with any different wells. You just have to replace everywhere in our paper. We usually use like Fonseca-Tartar. Everywhere we cite Fonseca-Tartar, you cite Waldo, and change the formulas a little bit. So it's not a huge issue. So you have this energy, and it's pretty well known, or it's pretty classical at this point, that that this goes to a sharp interface limit of a surface tension with a perimeter. And so how do we add homogenization to this? Well, as we saw a couple days ago, you could add homogenization to to the singular perturbation. But what we want to do is pretend that each fluid or part of the fluid has its own separate free energy. So we want to homogenize actually in the W and not in the singular perturbation. So, okay, so what are some cases that have been studied? So you have this epsilon, when epsilon is similar to delta, because the limits will depend on how these rates happen. So when epsilon is similar to delta, then Riccardo, Irene, Adrian Haggerty, and Cristina Popovici already studied that you end up getting this anisotropic surface energy. And it was recently extended to the stochastic homogenization case by Roberto Marciani earlier, I guess maybe last year. And so you end up getting this sigma, which is sort of like a lattice mismatch in that it encodes how your interface matches the periodicity lattice. And so you get this thing. But what I want to talk about is actually this case, which is delta. So the case that has actually been done is delta less than epsilon to the 3/2. And this was, I guess, the first trick, which is also in the Ancini Brides Geodesic, but also in this Brides Fieri. And then later, Adrian wrote a short note where basically you do it in the whole vector value case. And you can prove that essentially you get this splitting of scales. So when delta is less than epsilon to 3/2, you can view it as delta is small, so I'm going to send delta to 0 and homogenize first. So you have like a W home, and then you do the Modica-Mortola in this thing. So this is a classical type of thing, but there's always this 3/2. And why do we get 3/2? And it's mainly because of this very cute computation, which, okay, I do it through the unfolding operator. I don't think the original papers use the unfolding operator. But basically, this thing you can write as the unfolding operator minus, okay, W home, plus the extra boundary term, which is something small. And then if you assume W, if you hand wave and assume W is smoother, then this is of order this. And then, okay, the unfolding operator has a nice Poincare property that allows you to do this. And if you have that your sequence is bounded at energy, then your gradient, just by using the property that the unfolding of the gradient is the gradient of the unfolding in the y, up to some delta powers, you get this. So in total, you get a delta n over epsilon n to the 1/2, which is nice, in that this goes to 0. But the problem is that in your actual problem, when you're replacing, you have an extra epsilon. Right? So you end up getting this 3/2. And then, okay, so if delta is less than 3/2, then these two are equivalent. But what we want to show is that this is actually true even when delta is just less than epsilon. So there's nothing special about 3/2. And you can do this with epsilon. And this is something that we finished a couple months ago, and we're editing, and then we thought we would have it out by now, but the Christmas break, we didn't finish the final, the final bits of edits on this. And then I just wanted to mention that this epsilon less than delta case is open and is, I guess, free for people to consider. But you would maybe expect some sort of anisotropic surface energy, because you think of it as, I'm going to take epsilon to 0 first, so you get some sort of interface, and then which depends on x over delta, and then you want to homogenize some interface which depends on mu in some way. So the first thing I want to talk about is this result, that you can actually do this for any delta less than epsilon and not just epsilon to 3/2. And so what assumptions are we using? We have the usual assumptions that W is continuous in the phases, and it's measurable and Q-periodic in the spatial variable. So we want to allow for inclusions, and then that it has two wells, and then the usual coercivity and polynomial growth conditions that you have in homogenization problems. So what are the key observations that really allow us to do this? Well, the first thing is that this inequality, that yeah, grad y u delta n is bad, is nice, but it's bad if you add an extra epsilon, but you're allowed to add an epsilon to the 1/2, and that's actually given to you by this grad u n. Right? So that this product is nice in that you can send it to 0. And then the other thing to observe is that the lim-inf is really the problem, because the lim-sup, if you do the computation out with the recovery sequence for this, the usual Modica-Mortola recovery sequence, it actually works out. So it's never, the lim-sup is never a problem, it's always the lim-inf that's a problem. And okay, so this is sort of how to create a lower bound. So what we do is we first unfold in the first variable, and then if you define your unfolding to be one of the wells in the extra boundary region, you actually get this, and then you throw away the extra boundary term because it's non-negative, so you get a lower bound by doing this. And then, okay, we want to get these products out, so let's do the Modica-Mortola trick. And it's more, I guess, maybe more intuitive if you view it like this, where you have un plus something small, or something that's going to 0 in L2, or L1. But multiplied by grad un. And the idea is that ideally you'd want to replace this with W home, but it's, which means you want to basically say this doesn't exist, but you can't quite do that. For many reasons, mainly that the square root is not Lipschitz, and you also don't have any Lipschitz conditions on W, or we want to avoid using those Lipschitz conditions on W. So the idea is that you want to actually you want to give yourself some room, some eta, and then you want to say that we have a cell formula that it's actually below. That's below this thing. And how do you, up to some small term which goes to 0. So how do you define the cell problem? It's somewhat intuitive and somewhat just because the calculations tell you how to do it. So the intuitive portion is you'd want to do something like this because this is the form you had in that you had. And okay, this extra term, this is the u delta n minus un, is something going to 0, so you'd want to truncate to make it uniformly going to 0. And you'd also want to sort of modify at the boundary so that it doesn't, so as you're on the boundary. And the reason why you want this is because you want to say that W eta is still a continuous double well function that you can use all the classical results for, basically. And then this extra thing is because you want to say that this has a minimum, and really this is just because you have to choose, when you do the slicing argument for this, you need to choose your slices appropriately, and you want to choose it in a very measurable way, and this one actually works nicely for consistency. So what you can show is that with these properties, you have that the income problem is a admits minimizer. It's still a nice double well function, and when you let eta go to 0, your W eta goes to W. And so the strategy for the lim-inf is basically to say, okay, so the other thing I should mention is that over here, this is the strict lower bound. So we're not using any convergence properties here. So once you have something like this, and because it's a double well function, a normal double well function, you can use the Young measure tricks of Fonseca-Tartar to say that since you have this bounded, then the compactness result of Fonseca-Tartar holds. And so you actually get compactness for free from this lower bound. So then you have that un converges strongly to u, which is a BB function, which is only living in A and B. And okay, so then you get this, and you have, again, Fonseca-Tartar tells you that this is a sigma eta times the perimeter, and then you want to let eta go to 0 to get to your sigma home. And out of all of this, so these are the two main things you have to prove and that are non-trivial to prove, I would say. So the first thing, how to prove the first inequality, is by the slicing method. So as I said, we need to first do this radial truncation up to some eta. And so what you do is you truncate the function that we have, the extras u delta n un minus un, and then you use the slicing argument to say that in each q, so y lives in this q, and you take a cutoff function, which is 1 inside, and then 0 on the outside, and then, okay, goes from 1 to 0 and nicely along this set k, along this distance k. And this is what I meant about you need to choose your k appropriately, is that now our k is a function of x, so you need to make sure that this still stays measurable when you choose all your parameters here. And okay, and so you can do that. So it's why we chose our cell problem the way we did, is because it allows us to choose our kn in a nice, consistent way and a measurable way. And this works because basically what you can say is that up to a very small set, this Wn lives in this admissible set for our cell problem, and then this small bad set is actually contained in precisely this set. And okay, by Chebyshev's inequality, you can basically, you again get out this product up to some constant depending on eta and other terms. You got this product that we said was good because you can set it to 0. So the error is always goes to 0. So this is why you can do that first inequality, basically. And then the second inequality is actually quite tricky. And it requires this very deep paper of Zuniga and Sternberg from 2016. So what they do in this paper is they prove so in this paper they don't have any etas, right? So they just have some conformal factor here. And they prove under very general assumptions, so they only need that whatever factor you have here is continuous, and that it has finitely many wells, and that it goes to something non-zero at infinity. So as long as you have that, you have a minimum in this class, which is that it's Lipschitz outside of any arc which hits your wells. So what they basically shows that, okay, this is a metric and length space, but they mainly show that the minimizer exists. And the very key idea in this paper is that, okay, usually when you choose minimizers, you have an infimizing sequence, and you want to create some compactness to get some limiting geodesic. And usually what people do is they usually use some properties of W, like WC3, positive definite, to use the Euler-Lagrange equations, and eventually say that it's actually compact in the Euclidean metric. And so you can actually get compactness that way. But the key idea in this paper is that what's the point in using the Euclidean metric? We should be just using the metric that you have. So you basically show that the properties of Arzello-Scoli hold within this degenerate metric. And so they proved this, and then they proved that, okay, once you have Arzello-Scoli, then you get compactness, and then you can do some stuff with the length functional to get that this is actually a minimizer. So we're going to use this idea to also do this problem without using any other assumptions, like assuming WC3 or something like that. So the way we're going to do this is, okay, so Zuniga-Sternberg guarantees that we have a minimizer for each eta, right? So you define a new metric, which is D naught, which is the soup of all your metrics. And so what you show basically is that the hypotheses for Arzello-Scoli are satisfied for your sequence of minimizers in this metric D naught. And the key thing to use here is the fact that D eta is an increasing sequence of metrics, so it converges to your D naught since it's your supremum. And okay, so you can do that. And then once you have this, you always have this one for free. That's like, since everything is bounded by W home, you have this one for free. And then this one is the hard one to establish, but you basically use the fact that you have uniform convergence and the fact that there is a way to write this functional in terms of the length functional because it's a length space. And then once you have this is another inequality you can establish because W eta in some sense, is since it's the soup of all your etas, it's also it's close to your W home. So this one. So the main, really, the technical part is in this one, but it's not too bad since, okay, you follow, I guess, some of the ideas from the Zuniga-Sternberg paper, and you end up getting this. Okay, any questions on this portion? Okay, now we want to go to these lipid Rafts types of model, where you have this thermal fluctuations and thermal dependence. So you have what I guess people sometimes call nonisothermal phase separation, or I guess more recent in the physics literature, it's also called like a thermodynamically consistent Cahn-Hilliard. So these are some physicists who proposed this type of model from the 1990s. And basically, their main thing is that you should have this extra parameter theta, which you can think of as a temperature, and you should be studying this sort of functional, where W depends on both theta and U, and even potentially your transition layer length also may depend on theta and U. And a classical example of this is, for example, if you have W as some double well function for theta less, or T time, or temperature less than some critical temperature, and then above some critical temperature, there's only one phase. So this is, I guess, an example that the physicists really like to think about. But we're going to try to avoid some of the complications of having two variables, or two functions. And we're going to pretend we can fix a theta of x, so we're going to treat this as a W of x and U. And then we're also going to fix epsilon so it doesn't depend on all the fields. So surprisingly enough, I guess, so I started this as part of my PhD thesis, and surprisingly enough, it wasn't actually done. There wasn't much literature on this. So Sternberg, in his original 1988 paper, he does a special case where the wells are 2D graphs and you have very smooth W's. And then Bouchette showed a sharp interface limit in the scalar case. But the methods don't I guess, generalize to the vector-related case. And then the way I learned about this more so is through Riccardo and Giovanni Gravina, who was also a student at CMU, who was a student of Giovanni Leoni. And so what they showed is that they showed the vectorial case, but they had some extra assumptions on the wells, which Irene didn't really like that much. So what we do is we show a sharp interface limit under this much weaker growth assumptions, which is pretty much analogous to the Fonseca-Tartar assumptions. And precisely what the assumptions are is that we assume W is locally Lipschitz in the product space. So this is something that's a bit weird because usually you want to assume maybe only measurability in the X variable, but because of these geodesic problems that always come up, it's kind of, or we don't quite know how to deal with the full measurable conditions on X here. So, okay, and this time the non-isothermal portion is characterized by this fact that you have wells for two graphs, A of x and B of x, which are locally Lipschitz. And then this is our better restrictions, that W is in between two quadratics. And then you have a coercivity result. And then, so the way that our result really is different from the Cristofori-Gravina is that what they assumed is that you have exactly quadratic near the wells. So you have two quadratic functions, and you do it. So what is our theorem is basically that what you would expect in that you have a geodesic type of energy, where you take this square root, which measures the transition from, I guess, between your jump points, and U is only something in BV with values with A of x and B of x. And you can show that this thing is now your sharp interface limit. So, and the proof outline is that the lim sup, again, is essentially the same as the Ricardo's and Giovanni's paper. And really, again, the problem is in proving the lim inf. And so we do the blow up a little bit differently, but essentially it comes down to proving another convergence of geodesic problems. So you want to take the limit as this m goes to infinity of this thing, which, okay, if you close your eyes and look, you can rho mt goes to 0, so you'd want to say, okay, this goes to this, but it's much trickier than that. And so the way we do it, since we don't have a Zuniga-Sternberg paper for this case, because, okay, I guess I should point out in that is that this is not exactly a geodesic problem, because this problem is not parameterization invariant, because you have this extra t here. So it's not parameterization invariant, and so this is not a geometric problem. So what we do is that we make it a geometric problem by essentially minimizing over this extra portion that we want to send to 0. But this is at the cost of now your wells for this f are basically like a of x prime t, so it's not just 2 points. It's the entire graph, let's say. It's a of y plus epsilon. So what you want to do is that you want to foliate your space with these level sets of f epsilon. And I guess the construction you can make, because of the fact that we're in between two quadratics, we can't, even though we can oscillate, we can't oscillate too much. If you set a construction, you can use this to generate bounds in the equated length within each of these level sets, and then take the sum. And if you can prove that the infinite sum is actually converging, then it's nice. And so this is the construction. So what you're seeing here is that this is your 0 set. So like a of y prime, or y with the last column yn plus epsilon, or any t less than epsilon. Then you can theoretically have some infamizing geodesic, which is oscillating very badly around this. And this is the level set that we created. And what we do is we take the entry point and the exit point in your level set, and we just project them into the 0 set and connect them using a line. And what you can show through many applications of the co-area formula is that this actually gives you a converging series. So now we can think about adding homogenization to this, which is what we wanted to do in the first place. So really the only work that we know of for these types of wells, jumping wells and things, is this Zepier paper from 2009, where they give a gamma expansion where you have these wells are basically jumps from 1 minus k to 1 plus k, and then minus 1 minus k minus 1 plus k. And they give a characterization of all the different regimes for this. And we want to sort of follow this idea as well, but okay, in the vector valued case, it's kind of, it's not completely trivial. We don't have like an explicit form, so we can't calculate what the minimizers are. So it's not completely clear what to do in these cases. And mainly because there is some minimum energy to this, some non-zero minimum, and that you have to subtract out and then re-normalize appropriately. So these cases are also still open, I'll say. But, okay, and then to also, I guess I should mention the assumptions that we have on W, is that now we're taking our W to be the usual, cube periodic and all this stuff. But within within each cube, we're allowing our wells to jump. So we have this chi-ei, which are piecewise affine partition of your cube of just the usual, I guess, nicer W's. So this is, even though in our theorem, we can't allow W to be only measurable on X, we can sort of get around this by using this to be our extra measurability condition. So you can allow conclusions, but probably nothing more general than this without a more general sharp interface limit theorem. Okay, and then each one of these are the nice W's that we had in the sharp interface limit. So as I said, for delta less than epsilon and delta similar to epsilon, the vector rescaling is unknown. But okay, for epsilon less than delta, this minimum is actually 0. So you can try to figure out what the rescaling should be. And the way we do this is through this very heuristic scaling analysis, which is, okay, so if you have jumping wells, which is the case we're considering, you have to have these microscopic interfaces. So if you remember from our Lipid graph pictures, this is the microscopic interface, I guess. Even though they look more like honeycombs, we chose to do this just to be more general and not miss any effects in case there were any extra effects. So you consider this type of thing where you have some A of X here, B of X here, you have an interface which connects them, and then a cutoff region which connects them to the next cell. And then, okay, so if you periodize this, so if you take any Q and you periodize this in mu, you get this energy, where each one, I color coded to say where each one comes from. But basically, something to notice is that if you divide by epsilon over delta, which is also actually the scaling that you get in the brightest of Fourier paper, is that the first thing is you never see the bulk energy because the bulk energy goes to 0. And you only see these interfacial energies that you have here. And they have this, I guess, this Modica-Mortola form in that you have something inverse plus something. So you're forcing everything to be constants here. So the right scaling, per se, is epsilon over delta. And now this is where our analysis sort of diverges from brightest of Fourier, in that now we use this notion of two-scale gamma convergence, because it's actually, you'll see, it seems to be appropriate for this type of problem. So what is two-scale gamma convergence? It's basically just the usual notion of gamma convergence, except now you're doing everything in the two-scale topology. So you say, have limit inequality, say that for every sequence which strongly converges two-scale to U, then you have the limit inequality. And okay, I guess the critical thing here is that now your limiting energy lives in the double space. So it's not a function of x, it's a U of x and y, or U not of x and y. And then you also still have to do the recovery sequence. And this still has the same nice properties, though what I would say is that there is actually something interesting about this in that all the applications that I've seen of this, so especially in the Strudantsov and Chernyshenko paper, so it's usually a bit difficult to prove this strong two-scale convergence. It's easy to prove weak two-scale convergence, and sometimes, but you rarely see the strong two-scale convergence. But even if you don't have compactness, you can still obviously always consider the gamma limit with anything. But something that Strudantsov and Chernyshenko show is that for some problems, especially high contrast problems, even though you don't have compactness, you can show that the infimums converge to the minimum of your gamma limit. So usually the theorem in, I guess, gamma convergence is that if you have compactness and you have the gamma limit, then the minimizers converge to the minimizers. But with two-scale convergence, sometimes in some problems it's nice in that you can say that the infimums converge to the minimum of your gamma limit, even if you don't have the compactness of U epsilon converging to U strongly in two-scale. So this is an interesting, I guess, remark, but this might be one of the only cases that I've seen, because I've actually used this two-scale convergence for also a high contrast problem where we don't have compactness and we still get the splitting. This might be the only example where you actually do have the compactness and can actually show it. And why do you have this compactness? Because if you, okay, so you have this energy, right, which looks like, I don't know, or there's no special form to it that you think about, or I would think about. But if you unfold it, you can see that this has exactly this Modica-Mortola structure in the cube, where you have something small here, and then 1 over that something small. So it becomes a Modica-Mortola in this product space. And okay, so you can prove the usual theorems about, okay, this is converging strongly in 2 scale to something which is only a of y, g of y, and you get a gamma limit which has this, so the critical thing is that there is this volume energy, so it is a volume integral over all your microscopic interfaces. Okay, you have to modify how you define your dW a little bit since we allowed for jumps, but the formula is complicated and not really that important to this. So what this shows is that in this case, you can have microscopic phase separation, but no macroscopic phase separation. And you see these microscopic interfaces. But there is a caveat to this, in that this limit is only really non-trivial if your welds are jumping. Right? So if your welds aren't jumping, then this limit will just give you 0, like the minimum value is 0, and you have to go to the next order. So this is, for example, the case when you have just constant wells. Then you need to go to the next order, which is probably epsilon, or you have to do 1 over epsilon, which is still an open problem in the fixed well case. So you have this. So my question to biologists would be, why is your temperature jumping? I don't know. Or why not? Or is there a more mathematical model for phase separation where even when your wells aren't jumping, like your temperature isn't jumping so much, you can see this sort of microscopic phase separation, but no macroscopic phase separation type of thing. Okay, and so you have there's all these bunch of open regimes, and something we've been thinking about is thinking about how to do this with stochastic homogenization, especially because, as the biologists say, that the nanodomains are really caused by thermal fluctuations, so you would have to have some sort of statistical noise into that type of problem. And then, of course, there's the problem of what to do with dynamics for these types of energies. And Roston, Marine, Raghav, and Jessica Lin have been working on this problem for the epsilon similar to delta case of the convergence of the gradient flow for the homogenization problems. And then I always add this. We have Amit in the audience, so we always add this as you want to try to figure out how to do this sort of thing for more general first-order linear operators, especially when you have a curl here. So you have even the simplest Modica-Mortola for a curl, and not just for a gradient. Yeah. And that's it, I think. Yeah.